Okay, so today we are going to prove that very strong disorder holds at all temperature in dimension 2. Okay, so very strong disorder for D equal to. Okay, so what's the theorem? If D equal 2 and beta belongs to 0, 1, then f beta is smaller than minus exponential minus c over beta 4. Okay, so well, there exists C. Yeah, so the restriction to beta belongs to 0, 1 is just because here this is a bound which is only relevant if beta is small. Okay. Okay, this bound is not sharp. Okay, in the sense that you can get something slightly better. So. 17. What you have is that, in fact, f beta is equal to exponential minus pi over beta square 1 plus little o of 1. Okay, so realize that unlike what we had in dimension 1, okay, this is not really an asymptotic equivalent. This is an asymptotic equivalent for the log. Okay, so perhaps next time I can give you an idea. I mean, I didn't prove you any lower bound in dimension 1, so maybe we can do it in dimension 2. Show that like exponential minus c over beta square is a lower bound here. Because this is relatively easy. Okay, so yeah, what should we do, basically, to prove this? Well, we want to show that f beta is smaller than minus 1 over n, okay? For n, okay, which is equal to, well, exponential. Yeah, here I guess I should put a big C because this is, we are going to prove this with a big constant, right? Let me see, yes. I mean, like, the bigger the constant, the smaller this is, the weaker the bound. Okay, so for n equal exponent C over beta 4. Okay, and our way to do this is to bound the expectation of square root of W n m. Okay, where n is fixed and m is going to be arbitrary. Okay, and if we show that, well, yeah, that this decays like exponential minus m over 2, or faster than exponential minus m over 2, then we have this. And we're good. So prove. Okay. So yeah. So we have, the idea is a bit similar. But some things that have to be modified. So, yeah, the picture is the same as before, except that now my patches, they are two-dimensional. Okay? So, I without an arrow will be I1, I2, which belongs to ZD. Okay? BI. Okay, but I'm never going to use this, so therefore you can forget about it because right now, I'm going to introduce a conflict of notation where I1 and I2 are going to be different things. Okay. BI is just I square root of n plus 0 square root of n square. Again, n is a square by definition. Okay, so that square root of n is an integer. Okay, n is a squared integer. Okay, so you just round this to the next square integer. Okay, and now I is equal to I1, IM. Okay, and all these things are elements of Z2. Sorry? Okay. This is a subset of R2. Okay, but you can imagine as a subset of. Yeah, this is a translation of this box by this amount. Okay, yeah, this is if you prefer, this is. But you see, this is annoying already because I said I didn't want to, but this is this. Okay, but let's forget about it and never use this I1 and I2 again because I want to use them here. Okay, so now I defined AI to be the set of x's such that for all j in 0 m x, j, n belongs to B, I, j. Okay, and I0 is equal to 0. Okay, so this is really a partition of my set of trajectories. And I define W, N, M, I to be the sum over I in Z2 to the power M expectation of square root of W and M. What am I writing? No. I'm sorry, I need some more coffee. I just pulled a few lines in my notes. No, this is the expectation with respect to the simple random walk of the usual thing, the sum from n equal 1 to n beta omega n xn minus beta square over 2. I mean, again, we are considering that environment is Gaussian. This has just the effect of simplifying just a couple of things in the proof, but nothing essential. And here I put the indicator that X satisfies AI. Okay, so as a consequence, I have W and M is equal to the sum over I in Z2 M of Z and M W I. Okay, and you can apply the square root subadditivity here. So what we have is that okay, so I think for the moment being we didn't do anything new. We just wrote in 2 dimensions the decomposition we had last time. Okay, so now what's the strategy? Well, we want to apply, this Cauchy-Schwarz trick here. Okay, apply a change of measure okay, or well, like apply this Cauchy-Schwarz with a GI that kind of follows the blocks, and then kind of perform a factorization to basically limit yourself, well, to just get this finite volume criterion. You will just have to prove that some quantity is small, okay, instead of proving that something decays exponentially. Okay, so. Okay, so I will do perhaps some comment later on that, but okay, here when you apply this inequality, basically this inequality is an equality if G is proportional to 1 over square root of WNMI. Okay, but the problem is that if you do this, okay, you don't lose anything in the inequality, but you cannot compute stuff. The reason why we do this is we want to be able to compute stuff. So the idea is, yeah, to put with something which is, yeah, a bit like 1 over square root WN, but which will help you to do stuff. Okay, and so now I will kind of yeah, tell you what kind of GI we use here, and yeah, in the end, I will try to justify the choices and the choices we had in dimension 1. Okay, and now we are going to have a perspective which is a bit more similar to this thing of, well, looking at a likely event for the unlikely event for the original measure, which is likely for the size-based measure, but we will do it separately for each block. Okay, so okay, GI, it will be, well, the product from J equals 0 to M minus 1 of G J I J. Okay, well, we will define first G, okay, which will be G00, 0, and then we will say that G J I will be simply no. I'm going to define 0, 0. I'm just saying that now I'm just saying that I'm going to define things per block and in a translation invariant fashion. This is the only thing I'm saying here. Okay, so these things are just G0, but where you're considering the shifted environment. Okay, so you're shifting things by, well, if you're really considering a shift, you're in fact shifting by minus Jn in time and minus I square root of n in space. Because you're taking that point to the origin. Okay, so yeah, now before choosing G, let's try to see what we are going to have to compute, and then try to understand what G will be convenient. Okay, so what we have to compute is the expectation of GW. Okay, you have already seen the computation before, so W and X, Xn in BI. Okay, this is typically the thing we are going to have to compute. Here, W and X is just EX of whatever. Okay? So we want to be able to show that this is small uniformly in X in B0. Okay, and this thing here, if you remember, you don't care about it that much. Okay, because in the end, we will take it away. Okay, so, well, here you can basically use Fubini to compute that, and what you get is, well, EX, okay, this thing stays here, indicator Xn in Bi, but this is not super important. And here you get EX G omega. Okay, where we call dpx is equal to exponential sum from n equal 1 to n beta omega n xn minus beta square over 2 dp. Okay, so basically, what we want is the following. We want G. Well, okay. We want this thing to be not too large. Okay. And we want this thing to be small. Okay, and we want it to be small for most x's under this measure for all possible starting point in the box. Okay, so we want G to penalize an event which is atypical under P, but becomes typical under Px for most x's. Okay, under Px for most x in B0. Okay, so this is just to get an idea of what we should do. So here I will give you the form of G. So G, I mean, I'm just telling you, we want to penalize some events, so I can take G. G of omega, which is equal to, well, exponential minus m indicator an of omega. Okay, where an is some event. Okay, so the first thing I'm going to sort out is what the value we should take for m. Okay, because this will be guided by the fact that we want this to be small. Yes, okay, and afterwards we will proceed. To try to find some event that coincides. So So what we have that the expectation of gi omega. Okay, this thing is nothing more than the expectation of g omega to the m. Okay. So Fn measurable event. So yeah, this assumption makes all the blocks independent. Okay, so therefore I have this. Okay, because here I'm using independence and translation invariance. Okay, I have defined this as a product, and by this definition, okay, the fact that the other g ij they are defined via shifts. Yeah, it makes all the g's independent. In all the ANs, all the shifted version of the ANs independent, so all the g's are independent. Okay, and the expectation of g omega, well, it's equal to g omega. Sorry, I want this, right? This is what I'm interested in, and this is just 1 plus p of an exponential m minus 1. Okay, so just take m is equal to minus log Pn. Okay, and we are going to be good. Okay, but we want and we want Pn to be small. Okay. Okay, so now it's time to choose An. And basically, yeah, so this is B0. This is M. And basically, what I'm doing when I'm considering Px is I'm shifting the value of the environment by an amount beta along a random trajectory x. Okay, and I want to be able to tell the difference between this measure and the original measure, but I'm not able to use any information about x. Okay, that's the point. I want this test to be uniform over all x, all trajectories and all starting points. Okay, and I want it to work for most trajectories. So, yeah, one possibility would be to try to check on, okay, I mean, first, we are going to to look at an event that depends on yeah, so some box, okay, of width, big O of square root of n, and of length n, because this is where the trajectory goes. There is no reason to look outside. Yeah, if I look at the average of the environment here, yeah, there will be a problem because basically, yeah, the shift that I get to the sum of the variable, it's kind of lost in the natural Gaussian fluctuation. So this does not allow you to get a difference. Okay, so the idea is that we have to look at something that has to do with the correlation of the variables. Okay, and this is where we can introduce the variable yn. Okay, so what is yn? Okay, so it's a sum over n equal 1 to n over 2. Then a sum over k equal 1 to n over 2. Then I have a sum over x. Okay, so let me call this interval I R n. Okay, I R n is just the same interval as before, but I think it might be more convenient to write it as this. So it's just minus r square root of n, r plus 1 square root of n. Okay, this is just the big purple block I'm considering here. Then I'm summing over y. Okay, so y is in Z2. And then instead of considering omegas, I'm considering product of omegas. So I'm considering here omega n x, omega n plus k x plus y. Here, I want to divide by k. Okay, and the reason why I want to divide by k is that basically I want to multiply this. Okay, I want to have that this thing, the weight of this should be the probability that should be proportional to the probability that I visit the 2 points. Okay, so okay, the probability that I visit this point, it's kind of uniform. Okay, it does not really depend on x or n, simply because initially I kind of have to consider that the probability is uniform over the box. Okay. But this thing here is not uniform, and okay, I could take something else, but this turns out to be convenient, and this will simplify the computation. But basically, this is a kind of rough approximation of what the Gaussian density is. Okay, it's kind of constant on something of size square root of n, and basically very small as well. The square root of k, sorry, so it's square root of k. Okay, so yeah. This thing here is just the probability of transition for a random walk from that point to that point. Okay, and now, well, this yn, it's a centered random variable under. Okay, just because these variables here, they are independent central Gaussians. The event we are going to look is a deviation event for yn. Okay, and to make this atypical, well, I mean, this is not a crazy random variable. Okay, so we are just going to compute the second moment and say, well, something atypical will be to be much larger than the standard deviation. Okay, so this means that we have to compute things. So what's the expectation of yn square? Well, you see, I have a big sum, but okay, the terms are not independent, but they are they have okay, these different terms have covariance 0. Okay, just because if you have one omega that appears only once in the product, then the expectation is equal to 0. And okay, so, and if you look at the diagonal terms, they give you a contribution 1 because we have standard Gaussians. Okay, so this thing is just this sum and equal 1 to n over 2. Okay, here. n over 2, n over 2. I mean, it's just, I'm not going to lose anything by dividing the range by 2, and this allows me to have a range here that does not depend on k, and a range here that does not depend on n, so it's kind of convenient. Okay, but there is nothing super special here. Okay, sum over x in I or n. Sum over y in z2, 1 over k, indicator then y is smaller than r square root of k. Okay, yeah, r here is going to be a large parameter. Okay, it's one of the many parameters that we will have to choose. K to the power 2, thank you. Okay, so let's compute things up to constant. Okay, but I want to keep a trace of r. Okay, so yeah, what's this sum here? The sum over y. Well, I'm summing over the ball of radius r times square root of k. We are in dimension 2, so I get this, okay, this, and this. Is this okay? Okay, then it's easy. I multiply. Okay, this is times n, this is times n, and this is times well, square root of r. N. Okay, because we don't care about no. R square n. Yes. Okay, because we are in dimension 2. So okay, so what we get in the end is something of order r to the 4. Oh no! I'm really sorry. No, this gives you log n, right? This gives you log n because I'm summing 1 over k. Okay, so what we get is r4 n square log n. Okay, so the event we are going to take is yn larger than r3 and square root of log n. Okay, and we get that the probability, this is an, and the probability of an, well, it's smaller than a constant times r to the minus 2. This is just Chebyshev. And this is, yes, this is not this r, this is this r. Okay, I have R4, which is divided by R6. Okay, why taking yn large instead of yn small here in our event? Well, you can see that when I'm going to shift my variables by beta, okay, I'm just adding some beta here, and this will make at least the mean of yn larger. Okay, because it will replace some terms here by terms of mean beta square instead of mean 0. Okay, so yeah, the effect is not completely monotonous, but yeah, it goes toward the direction of making yn larger. So okay, so yeah, this gives us also the value of m, okay? Like exponential minus m it's really r minus 2 as well. Okay, exponential minus m is what we are going to get. Well, okay, it's smaller than r to the minus 2. Okay, any questions so far? Okay, so now we are kind of ready to well, try to compute the expectation of G, I, W, and M, I. Okay. Let's do it here. Expectation of Gi omega W and I. Okay, and now I want to make directly the factorization here. Okay, so what should I do? Well, okay, so yeah, it's the product, okay, from J equal 1 to M. Then I will get the expectation of G of omega. Then, okay, here I have the max over x in B0, okay, because this is what we need when we factorize. Here I will have E x exponential sum from n equal 1 to m and beta omega n xn minus beta square over 2. Okay, always the same thing. And here I have the indicator that xn belongs to b, I guess, ij minus ij minus 1. Okay, so how do I get this? Okay, just by, okay, you can get, yeah, I think the simplest way is by induction. So you write this down, you write what this is, okay, and then you kind of cut according to the value of x n times m minus 1, okay? And then in this decomposition, well, this gives you, you can use Markov property, so you can, basically you can cut your big partition function into 2 blocks. One block, you can bound it by a maximum like this, and you can factorize also the expectation with respect to the environment. So this will give you one term like this with exactly this thing you want. And the other thing, you can resum over x, and you get the original, but you have replaced m by m minus 1. Okay, so you repeat it, and each time you get. Okay, so now once we have this, we are good. We can factorize everything, and we just have our finite volume criterion. Okay. Yeah, okay. But perhaps I will try to give the details on this. Okay. Let me. That's a bit of writing, but. Okay, so yeah. Okay, so let me introduce a notation. I minus is just I1, I m minus 1. Okay, so what I have is that W n m I is equal to, okay, I have this exponential here, and here I can write this indicator A I minus X indicator X and M is equal to belongs to BIM. Okay, I'm just splitting this event into two things. Okay. Okay. And now I can rewrite it, okay, as the sum over X in over X in ZD if you want. And here I have indicator X n m minus 1 is equal to X. Okay, but this sum here, actually, I mean, because of this event here, it's really a sum over B I m minus 1. Okay, so now I'm using this to factorize. So what I'm getting is sum over X in B I m minus 1 E exponential of, okay, now I'm splitting things, so n equal 1 to n m minus 1, okay, beta omega n xn minus beta square over 2. Here I have indicator A I minus X. Here I have the indicator that X and m minus 1 is equal to X. Okay, and here I'm just using the Markov property for the random walk. So here you have then EX exponential sum. Okay, so n equal 1 to n beta. And now I have omega n plus m minus 1 n and x n plus x. Okay? And now I have the indicator that X n belongs to BIN. Okay, so then I'm considering expectation here. So I get that this expectation there is equal to, well, this thing time this thing. Okay, just because independent environments. Now, if I want an inequality, I can just replace this by, well, the max. Okay, let me put a y then. So the max over y in bi m minus 1. Okay? Then I can take away the sum. Okay? So this term here is just the expectation of w n m minus 1 I minus, okay, which is exactly what I want in my recursion. Okay, and this last thing here, okay, there is something I want to modify about it, which is simply, well, I want, okay, by shift invariance of the environment, I can already take this away. Okay, and now I want to shift y. So this corresponds to shifting space by square root of n times I m minus 1. Okay, so I would say this is the kind of result where, okay, there is nothing to prove. Like the difficult part is to make the statement up. If you make the statement up, you've already proved it. Okay, this is. Okay, so if you know I want to have a factorization, then you think what the factorization should be, and. Okay, then it's always better to check that you've not made mistakes, but things should be okay. Okay, so now everything is good because from this and from reorganizing terms, okay, what we get is that E of square root of W and M, well, it's smaller than yeah, so this thing here is smaller than 2, right? Because of this. Okay, I can just ignore this minus 1 here. It's not very important. Okay, so this is smaller than, okay. I have here the sum over I in Z2. Okay, let me put this here, G omega minus 1. Okay, and here I have max over X in B0 E G omega EX whatever. Exponential, the right thing, indicator xn in B. Okay, perhaps I should rewrite it now. Okay, Okay, I want to write this, okay, and this index will be I. Okay, it's just because when I write the sum of this, okay, I mean, what I want to have is really, I mean, the sum over, what I end up having is the sum over I in z to the m of the square root of this. Okay, and things factorize. You just have to rearrange these indexes. Okay, I make these my variables and then I factorize. The important thing here is that I can probably rewrite this as EX of G omega indicator xn in BI. Okay, so it's more compact, and second, it will be easier to work with. And I have square roots everywhere. Okay, this thing here is just this thing here. Let me write the intermediate term. Okay, so what I had is really the sum over I in z2 to the m times square root of exponential gi omega to the minus 1. Okay, so this thing is really this to the m, so I don't have any problem. And the second thing I have is the square root of EX G omega times the indicator that xn is in Bij minus ij minus 1. And here I have the product from j equal 1 to m. It's missing the max. Now it becomes obvious why I don't want to write things, because each time I write things, it's okay, so you have this sum. Okay, this thing, it's really, well, this thing to the m, so you don't have any trouble. This other thing, well, you just you say that this thing is just uj, okay? You make this change a variable, and then you factorize. And this gives you this sum to the power n. Okay, so you just have to show that this thing is small. We know that this thing is small. We want to show that this sum is smaller than 1 over. We want to show that this thing is smaller than we want to show that this thing is smaller than square root of than e to the minus 1/2. Okay. So we know that this is smaller than 2. So we want to show. Okay. We want to show that this thing is small. This is not important. We are going to be able to show that this is arbitrarily small by tuning the parameters. Okay, so we have to write to work on this. Okay, so first thing we are going to do is to show that you don't care about large i's. So the sum over I larger than A of the probability that xn is in bi. Well, this thing, well, this is smaller than anything you want. So let me take my notes because I've taken care about the constants in this thing. So I think 1 over 2e is good. Do you want 1 over 2e? No, 1 over 2e is not good enough. I think we should take 1 over 4e here. Let me recall what we have to show. Okay, so we want to show that the sum. Yeah, so I think 1 over 2 square root of e is probably good. Okay. We want to show that the sum over I in Z2 of the max over x in B0 E G omega x EX indicator xn in BI. We want to show that this sum here, well, it's smaller than 1 over square root of 2e. Okay, so 2 square root of 2e. Okay, this is what we want to show because we have a factor square root of 2 here. Okay, so this. Okay. So why is this true? Well, simply because, well, the probability. Okay, let's take I equal I1, I2, where I1 and I2 are larger than 0, and things work better in the other direction. So this thing, okay, Px xn in BI, it's smaller than the probability that, well, xn1 is larger than I minus 1 square root of n, and xn2 larger than I minus I2, I1 minus 1, I2 minus 1 square root of n. Okay, here I'm making this semi-infinity intervals instead of, okay, I'm just taking away the limit on the right. And what I'm also doing is, well, shifting by x and taking the worst possible case. Okay, so, and this is smaller than exponential minus I1 minus 1 over 2n square minus I2 minus 1 over 2n square. So yeah, you can see that even after taking the square root, this thing is summable if you take only large i's. Okay, this will be true. So okay, so this is true for a large. Okay, so now the sum we have to bound. Okay, okay, and this gives us a bound for the corresponding terms there because g here is smaller than 1. Okay? G is exponential minus m times some indicators. Okay, so yeah, now we have that the sum here it's smaller than 1 over 2 square root of 2e plus 2a plus 1 square times the max over x in B0 ex g omega. And here I should put some square root. Okay. Okay, so I just have to show that this is small. Okay, I want finally to show that this is smaller than 2a plus 1 to the minus 2 times 1 over 2 square root of 2e. If I can show that this will be our final set. Okay, and this is the most important one because this is the only one where we actually use, well, our choice for G, okay, which is basically the crucial input in the proof. Okay, so definition of Yn should stay. Yeah, so let me rewrite this expectation. Okay, so yeah, I have okay, E x g omega. Well, it's okay. It's smaller than exponential minus m plus p of a and c. Okay? I mean, this is equal to exponential minus m on an. And this is equal, and an has probability close to 1, so we're not losing much here. Yeah. So, and this thing, by the way, it's smaller than r to the minus 2. So by taking r large, okay, first we choose a, then we choose r. By taking r large, this is not going to be a problem. Okay, so really what we have to bound, so we need to bound Ex times Tx A and C. Okay, so now what we need to do is basically, okay, A and C is the event that Yn is, in a sense, small. Okay, so this event, remember, it's just, it's Yn smaller than R3 and square root of log n. Okay, perhaps. Okay, so let's compute the mean and the variance of yn under this new measure, and try to, so we will compute the mean, and we will bound the variance, because we are going to use Chebyshev. Okay, so I will call it mx. It's, of course, this thing, it's a random variable in the sense that it depends on sorry? Yeah, it depends on the trajectory, it depends on x. Yeah, okay, this is going to be a bit technical, so let's take a small break so that I recover a little bit, and we're going to compute this. Let's compute this, and let me write things a bit differently. So yn, it's really yn of omega, right? So perhaps it might be more convenient to write this thing. Okay, and here it will be some different omega. Okay, that depends on x. But, I will probably not write the dependence in x in the future, just to make sense. And what's omega x? Well, it's simply it's omega and x plus beta times the indicator that x is equal to xn. Okay, so so what I'm doing here is just replacing this by that. Okay, so now the important thing that when I'm doing this, okay, I get well, possibly the product of two things, but when I'm expanding, just the beta square term is going to be relevant because the rest have mean 0. Okay, so what I get is, well, a sum over n, a sum over k, then I get beta square, then I get, yeah, just beta square over k. Then I get the indicator that xn plus k minus xn is smaller than k than r square root of k. Okay, and then I'm getting the indicator. Yeah, I don't have to write it anymore. Yeah, I have this indicator here, square root of r. Well, okay. In I n r. Okay, so now the important thing here, okay, so basically you would like to say, okay, this is likely, so this is the only thing I care about. Okay, and this is something you can do, and in fact, this is something we could have done last time. So, yeah. Last time what we did was to say, okay, with large probability, all of these terms are simultaneously 1. Okay, now this is not true anymore, because this is not true for this one. Okay, but this is, in any case, not something we need. So, let's write this. So, let's write m bar of k to be equal to beta square over 2, beta square times sum from n, k, n equal 1 to, okay, beta square n over 2 times sum k equal 1 to n over 2, 1 over k. Okay, so m bar is basically the essential supremum of mx. Okay. Now, if you look at the probability, okay, over px, but this is going to be uniform in x. Okay, if you look at ex of mx, okay, well, this is divided by m bar. Okay, this is larger than the mean over k n of px x n plus k minus x n smaller, larger, smaller, so smaller. R square root of k and xn in I n R. Okay, the ratio between the two, it has to be, I mean, it's the same sum except that you have this probability here, so you can just replace this by the minimum. And okay, here I can take away the x if here I take xn smaller than r square root of n. Okay, and this thing is larger than 1 minus exponential, 1 minus 2 exponential minus r squared over 2. Okay, just because I'm just taking the union of these two, of the complements, and the complements, I mean, you know that this is the probability that xk is larger than r times square root of k. This. Okay, and yeah. Okay, so yeah, it's basically it's larger than 1 minus epsilon, where you can take epsilon. Well, this is epsilon. Okay. Okay, so for this reason, like the probability that mx is larger than m bar over 2. This is larger. Well, this is okay. This is equal to 1 minus the probability that m bar minus mx is okay. I'm yeah. M bar over 2. Okay, and this is larger than 1 minus 2 epsilon. Okay, this is just Markov. Okay, so 1 minus 1 minus the expectation of m bar minus mx divided by, okay, I have 2, I have m bar. So 1 minus 2 epsilon. Okay, and this thing, it's just beta square and log n. Okay, so all of this is good news. Okay, why? Well, because, okay, you want to show that, yeah, being smaller than R3 and square root of log n is atypical under Px. Well, you know that typically under Px, the average of yn is larger than n log n. Okay? So n log n is much larger than n square root of log n. Okay, and you also see where this beta 4 appears. Okay? Here, okay. This is going to be true if beta square, okay, does not, okay, if beta square times square root of log n is much larger than 1. Okay, meaning that you need beta square to be equal to, you need n, sorry, to be exponential c over beta to the 4 for some large constant c. Okay, so for things to work out, somehow you still have to control the variance. Okay, you have to say that the variance of yn under ex is not much larger than the original variance. Okay? Okay, so let me write before what we are going to do. So Ex, P, A, and C. Okay. This is smaller than Px, Mx, smaller than m bar over 2. Plus okay, so yeah, we know that this is small. Now we are going to show that this is small uniformly in X, just by using Chebyshev. Okay. 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 So this thing by Chebyshev. Okay. P, X, A, and C. It's smaller than the variance over Ex over Px of Yn divided by m over 2 minus, I guess, R3 n log n square root of log n. Okay, this is just Chebyshev, and I'm taking the positive part here to make sure that. Okay, so if we can show that, yeah, this thing is still okay. I want to show that this seal is still of order n log n. This was R4 n log n. So if I can show that this is still of order n R4 n log n, I'm good, because this C is going to be much larger. Okay, so now what I have to assume, I'm assuming that this thing is larger. Okay, is larger than what? Yeah, this thing is larger than 2 R3 n square root of log n. Okay. This is what I'm assuming, and this is exactly the same as saying that I think n is larger than exponential minus R6 over beta 4. Okay, but R is a constant, so this is really. Okay, so let's compute the variance and we will be done. Okay, so when you compute the variance, well, you're adding the betas here, so you're expanding, and okay, the beta squared term doesn't count because it's a constant; it doesn't generate variance. Well, for the rest, what we are going to do, I mean, we could do all cross terms, but this would be very fastidious. What we can do is to do simply the following thing. It is to say that, well, the expectation of A plus B plus C square. Okay, this is the variance we are trying to compute. Okay, we have 3 terms. Because here we have 4 terms, but one of them is constant, and the other, there are 3 terms of 0 mean. Well, this is smaller than 3 times the expectation of A square plus the expectation, well, B square. Well, okay, no, I'm just using this, right? Okay, so I will just compute the variance of the 3 terms separately. So what are my terms? What is my A? So A is simply yn, okay? I had yn of omega, okay, it's equal to yn plus 2 other things. Okay. Minus mx, okay. This is the square we are trying. So the first thing is yn of omega. The second thing is, well, beta, okay, sum from n equal 1 to n over 2, sum from k equal 1 to n over 2. Sum over y in zd, omega beta, then I get omega xn plus y. No, omega, sorry. K plus n x n plus y divided by k. And then I have the indicator that y is smaller than square. Because these indicators I will not, yes, this will be. Okay, and I have an indicator for x. Xn belongs to I and R. Okay, and I have another term that comes to the expansion where basically the beta comes from the second term. Okay, and okay, beta sum from n equal 1 to n. Sum from n over 2. Then I have, so there is no beta here. Omega yes, x in I and R, omega n x divided by k and then I have the indicator that x n plus k minus x is smaller than r square root of n. Is it correct? Yeah, I guess so. Okay, so this thing has a variance which is, of course, well, the same variance as before. Okay, so this is A, this is B, and this is C. Okay, so the variance of A well, it's smaller. Okay, it's of order. Yes, R4 n squared log n. Okay, this is the thing we already computed, and this is fine with us. And the variance of B and the variance of C, they are much smaller than that. So this is the point. So the variance of B. Okay, here we have only we have a sum of IID random variables. So when you compute the variance, okay, you get first you get a beta square that, in theory would help you, but you don't even need it. You can forget about this, okay, because this is one most of the time anyways. So okay, basically here you get this. You have this R2 over K. You get this, R2 times K divided by K squared. So you get this R2 over K. So this gives you a log thing here. And this gives you N. Okay, so you get N. Yeah, it's the thing that you don't have the sum over X. So this is the reason why it's considerably smaller. Okay, so you get N R squared log N. Am I right? Yeah. Okay, and the variance of C is the same thing. Okay, so the variance of C, basically, this point here is fixed. Okay, so when you sum over X, okay, you have at most R squared K possibilities. Okay, so this gives you your R squared over K. Okay, so overall what you get is that the variance of yn under ex, okay, well, this is smaller than C R4 n squared log n. And this makes all good because this will tell you that this thing here will be smaller than a constant times r to the minus 2. Okay, and so then you need to take R large and you're good. Okay, and this yes? Okay, so yeah, these terms, they tend not to be really important. Basically, the idea is that the variance you create, each term here brings you variance 1, okay? And basically, compared to the original thing, B and C, they contain only a very small fraction of the term. So for this reason, you gain a factor n, which is really huge here. So you don't need to worry too much. Okay, so perhaps some comment on why this works. Why is this yn so relevant for this? Okay, and perhaps I leave you breathe a little bit. You tell me when you're ready. Okay, so now we've seen the proof. So why does everything work, and where could the intuition for all of this come from? Okay, so well, let's look back at what Zn is. Okay, so Zn and Wn, they coincide up to multiplicative factor. So Zn, it's the expectation of exponential sum from n equal to n beta omega x n xn. Okay, and yeah, when you want to apply your Cauchy-Schwarz thing, you want basically to get simpler expressions, but that are somehow very correlated with the n. And one option you have is to look at the Taylor expansion of this. Okay, so this is, well, 1. Okay, so 1 is not really interesting. Then you get the second term, which is, well, the expectation of the sum from n equal 1 to n beta omega n xn. Okay, so let's forget about the beta. This thing, okay, the expectation of the sum n to n omega n xn. Well, it's nothing more than, well, the sum over omega n x, sum from n equal 1 to n, okay, sum from x in z d, okay. Okay, d is equal to 1 or 2 here. And then you take w n x, p, xn equal to x. Okay, and now, yeah, when you look at this, okay, this is roughly the sum we considered when we had to differentiate the two measures, the original measure for the tilted from the tilted one. Okay, so what we were looking at is really, okay, so in dimension 1, basically, we could be very rough and say, okay, let's say that this is just 1 over square root of n indicator that x is smaller than r square root of n. Okay, so this is a very rough approximation of this, but this is uniform in the block. This is uniform in time, so this is good. And in dimension 2, we did something like a bit smarter, which was yeah, 1 over n indicator x smaller than, well, okay, not exactly this. We had taken r, which was increasing with n for some reason, but basically, probably the best thing would have been to plug this. Okay, and then. Okay, yes, when you're combining this with the block argument, basically, you're losing information here about the starting point, so that this doesn't even work in dimension 2, okay, just because. Yeah, you can look at the second term, okay, which is beta square over 2, and here you will get, well, the sum over n prime equal 1 to n omega n xn omega n prime xn prime. Okay, and let's forget about the diagonal terms, okay, and let's assume that n is smaller than n prime, and forget about the 2 here. Okay, so now this thing here, okay, it's really, well, the sum over n prime x prime omega n x omega n prime x prime, and then you get this probability that xn equal x, xn prime equal x prime. Okay, and now, yeah, if you're using the block strategy, yeah, this first thing is basically uniform on the strip, but the second thing, you keep track of it, and this thing, okay, is really, this is a simplification of this probability. Okay, and yeah, so basically, yeah, why shouldn't you go further? And the thing is that, okay, in dimension 1, basically, you get beta to the 4 with the first term, and beta to the 4th is optimal. But in dimension 2, it turns out that, yeah, the further you get into this Taylor expansion, okay, so you can take yn to be more complicated, to be like a, yeah, this is already a quadruple sum, so you can take it to be a sextuple sum. And basically, yeah, taking more terms in your sum, getting further in the Taylor expansion, gets you an exponent which is closer to 2, which is the right result. And yeah, if you want to get the right constant, okay, and the right exponent, basically, you need to take the number of sums here that goes to infinity when n goes to infinity. Okay, it's not something very nice to do, and also you have to really replace this by the green function. But if not, things don't work. So it's a bit educative because, but in the end, you get some big sums that are really difficult to control, and you need to think about. Yeah, basically you need to do drawings to simplify sums. So, well, in a sense, I think this is a good trade-off, like to have the wrong exponent, but still a nice result, and going only to the second term of the expansion. Okay, so this was one consideration. Perhaps the second consideration is about something very general, which is this kind of block argument, and yeah, what you're trying to do when you're doing this kind of. So there is this thing that physicists called I don't remember in which direction it goes, but I think it's group renormalization. Renormalização de grupos. No, renormalization group. Okay, because it's a group, um grupo de renormalização. Okay, so it's not really a group. It's more a semi-group in a sense because it only goes in one direction. But the idea is the following. You have a model. Okay, so in our case, this is a directed polymer. Okay, so let's say that your time horizon is n. Okay, and here you can have a natural transformation of this thing. It's just you're just doing some scale transformation. Okay, so you consider this is a random measure on path. Okay, so well you're just going to say to replace n by 2n, but then divide n by tn, divide time by t, okay, and divide space by, okay, let me call this t, okay, and t becomes nt, and divide space by square root of n. Okay, so you've not done anything to your model. You're just looking at it from a different point of view, and also you change the value of the time horizon. Okay. And now you're saying, okay, what I want to know basically is whether this thing converges if I apply it repeatedly, or if, I mean, this is what you have. If you call this transformation theta t, okay, basically you have theta t prime is equal to theta t prime. Okay, so if you write it with logs, basically you get some semi-group of transformation. And you want to know whether when t goes to infinity, this goes to a fixed point. Okay, so one possible fixed point, okay, and the natural fixed point if you're actually applying this transformation is Brownian motion. Okay, because actually I think you should do some other rescaling. Okay, so this is not theta, this is theta n. Okay, sorry. Okay, so yeah, the question is, it's a dynamical system question. Well, except that your dynamics is in some very weird space. Okay, and it's not a very nice dynamic. Okay, but what you want to know is whether basically Brownian motion is a stable fixed point for this dynamic, or is an attractive fixed point for these dynamics. Okay, basically it's a fixed point. Okay, because I defined my rescaling so that Brownian motion is yeah, we want to know that if you have a little bit of disorder, so if beta is small, you run away from this fixed point or not. Okay, so the idea that we have when we divide things into cells, okay, is basically you want to know whether by considering a large cell, disorder gets stronger or weaker when you expand things. Okay, and what we have done here is basically showing that, in a sense, disorder gets stronger when you take the cells to be larger. Okay, and somehow, yeah, for physicists to make predictions, they can basically just look at yeah, the variance of the corresponding partition function inside the cell, and they say, okay, if this blows up, then this means that yeah, my disorder gets stronger when I iterate the transformation, and therefore I should run away from the fixed point. And in the direction, I will converge to the fixed point. Okay, so there are a few cases where you can make rigorous arguments with exactly this transformation, but these are quite rare. And usually it's more something that physicists use to develop intuition. But you can still kind of use this idea to make mathematical reasoning just by making these kind of block decompositions. Okay, yeah, I think this is where we should stop today. What I will do next time, okay, is give you a proof of a lower bound for the free energy, because this is quite simple, much simpler than this. Okay, so saying that in dimension 2, yeah, we get the bound that we get, it's negative, but it's really tiny in beta. But yeah, so it's off, but not by that much, okay, and it's not difficult to show that indeed the free energy is tiny in dimension 2, okay? So this is one thing, and yeah, the other thing we will do on Friday is, well, I will try to wrap up things also to talk about polymer questions that were not talked about during this this class. I will do this lower bound, this other bound thing. I will also talk about path overlap, so like localization properties, but outside of the endpoint, and basically to mention open questions, because this is something which is yet to explore. And then we will move on to another subject for the 3 last lectures. So basically, we will look at directed polymer on trees. So this is a case where you can compute exactly the value of critical beta. And what I would like to do is probably to explore the relation between this and branching random walks. Okay. Any question? Okay, so yeah, I sent a correction of the exercises via email, a solution. Yeah, I have to send it to